keep your questions ready. And Dhruv will talk to us about domain wall constraints on the doublet left-right symmetric model using PTA data. Thanks, Dhruv. Take it away.
So I would like to thank the organizers for giving me this opportunity. And so I'm going to talk about this domain wall constraints on the doublet left-right symmetric model using the recent PTA data. And this work is recently been accepted. So what is the motivation? Okay, so we have heard many talks that tell us that there was recently a compelling evidence of nanohertz gravitational wave background, which was found by the PTA results of these various collaborations. Okay, while the standard astrophysical interpretation is that of supermassive black hole binaries, okay, there are many cosmological models which actually fit the data better as compared to the standard interpretation. So one such example is the domain walls fitting the data, and the base factor is of the order of 10. Okay, and if we fit the gravitational wave spectrum with this domain walls, then what we find is that the domain wall tension is of the order of 10 raised to 5 GeV cubed. Okay, and the annihilation temperature is around of the order of 100 MeV. Okay, so it is impossible to source such a large domain wall tension using electroweak scale physics. So if we want some microscopic description, we want to look for a higher scale physics. And one very good, well-motivated class of models are the left-right symmetric models, because they have something called as a parity symmetry that we can impose, and which is spontaneously broken, and that produces domain walls, and it can give walls with large surface tension. Okay, and so what we are trying to do is that we constrain the parameter space of this particular version of a left-right symmetric model, which I call the doublet LRSM, using the PTA data. Okay, and this is a plot which I have taken from John Ellis's paper, which shows the various sources of the signal. Okay, so in the left-right symmetric model, the gauge group is basically, it has a SU2L, SU2R, and U1B minus L, and in addition, you could have a discrete parity symmetry, which I call P. Okay, and the idea is that in the early universe or at very high temperatures, the gauge group is actually, the universe is left and right symmetric, and you generate this electroweak or the standard model by a spontaneous breaking. Okay, so there are basically, the breaking happens in two steps, from GLRSM to the electromagnetic or QED. Okay, so now this scale, which I call VR, is a high scale, and these three scales are actually related to the electroweak scale, and there has to be a hierarchy between these scales, and depending on the kind of scalars you choose for the breaking, you could have different versions of left-right symmetric models. So one of the most widely studied ones is the triplet LRSM model, where there is a bidoublet and two triplets. Okay, and but you could also have a bidoublet and two doublets. In this case, this is what is DLRSM, and I am going to basically focus on this one. So as I said, there is a hierarchy of scales. Okay, and these three waves follow this relation. Okay, so why this DLRSM is interesting? Because in the last few years, people have written papers which show that the electroweak symmetry breaking mechanism can be very different compared to TLRSM. So that's what has made this interesting. So okay, so recently we calculated for this same model gravitational wave spectrum from first order phase transitions. So I have just written that. Okay, so now coming to the potential. So this chi's represent the doublets, while the phi is the bidoublet. We don't have to worry about all these expressions. What is important is that it is made up of three pieces, and assuming that you put a discrete left-right parity symmetry, So this is what you can write down the potential as, okay. And to get the desired breaking pattern, these are the wave structures that we need to impose. And also P imposes GL equal to GR on the gauge coupling constants. Okay. So now, why do we get domain walls? Because our potential is completely parity symmetric, so there is no need to have a hierarchy where VR is much greater than VL kappa 1, kappa 2. There could also be the other way around, where VL is greater than these three waves. Okay, and so that's why this indicates that there is basically there are two different kinds of minima. So let us call the parity breaking scale as V naught. Okay, and in terms of the background fields, we can then write down the effective potential, and the domain walls only form after parity breaking. So basically they would exist for a temperature range which is between the annihilation temperature and V naught. Okay, so somewhere there, and we can show that it, to a very good approximation, the effective potential will be just be like look like V chi, which is only given by the triplet or the doublet one, this contribution. Okay, and this has a Z4 symmetry, and it has 4 degenerate minima. Okay, and these points are basically saddle points. So the present universe, or the one which we live in, would belong in one of these minima, while the other three would be false minima, which basically we do not have, we are not in any one of those. So now we can have domain walls forming between these. Okay, so so basically there are two types of domain walls in this model, because there are basically adjacent minima and non-adjacent minima, and both are, as we can see, they have different distances in field space and follow two different equations. So so those I call Z2, which are relating non-adjacent minimas, and LR, which are relating the adjacent minimas. Okay, so we can write down the kink equations, which is basically a pair of equations for each of these types of domain walls, and we can compute what is the surface tension. So here I have shown a configuration. So if you take a domain wall configuration which is basically located perpendicular to the x-axis and at x equal to 0, so then these are the kind of profiles you would get. So this is for LR domain walls, and this is for Z2 domain walls. Okay, and this is the energy density profile. So here we clearly see that the LR domain walls, which is the solid lines, the energy is much less as compared to the left, right, the Z2 domain walls. Okay, and if we scan across the parameter space, rho 1, rho 2 in this plane, we see that the dimensionless sigma, which is just rescaled. So this actually is always true, like in the entire parameter space, Z2 domain walls have a larger surface tension. Okay, so from here, once we do this, we can find a parametric dependence of sigma on these three parameters. So V naught, rho 1, rho 2. So because of a higher surface tension, the Z2 domain walls are actually unstable, and they can decay into a pair of left-right domain walls. So if at the beginning the network looks like this, where you have both kinds of domain walls, so this is just a schematic picture, and it should quickly go to a network which only comprises of left-right kind of domain walls. Okay, and this probably justifies why like most of the papers, they only talk about left-right domain walls. They do not actually discuss much about Z2 domain walls. And after that, basically, we can get the scaling regime, and in the scaling regime, rho domain wall is just proportional to sigma times h. Okay, and because we know that, I mean, the walls cannot, they are not allowed by cosmology at late times, so we need to annihilate them, and the way to do it is to introduce a bias in the potential. And here I am just taking V bias as a new free parameter, so which ensures that the desired minimum is deeper than the other three minima. Okay, and that would this particular condition would lead to a definition of an annihilation temperature. Okay, now because this we want the walls to annihilate before BBN, so this will give a lower bound on the V bias. Similarly, we can find a upper bound from the fact that the stable minimum or those kinds of domains should not percolate. So now let me discuss the gravitational wave background. We know, we have seen in very good talks that the gravitational waves are emitted by these kinds of domain wall networks, and the dominant contribution actually comes from the at T annihilation, and this is the form of the spectrum. Okay, this is a shape function, and which goes as, I think, f cube for lower frequencies and as 1 by f for higher frequencies. Okay, and this alpha star is basically a rho domain wall normalized by the radiation density at the annihilation temperature. So what we have done is that we have now, for each of the parameter values, we have this omega domain wall gravitational ready with us. So we have used this to perform an MCMC over the NG15 data. That is the 15-year data set of the NANO-Grav collaboration. And we have taken two hypotheses. In one hypothesis, we are just considering that the entire gravitational wave background is caused by just the domain wall sourced by this DLRSM model. And in the second case, we also consider an additional background from the binaries. So these are the two hypotheses. So this is the kind of posterior distributions we get. And in particular, I mean, the V naught and V bias are very well constrained. The other parameters, which are rho 1 and rho 2, actually have relatively large ranges which are allowed. So I'll just show this. So these are the best fit plots. This is with only DLRSM, and this is I've just shown with DLRSM plus the SMBHB. Okay, and these are the 1 sigma and 2 sigma bounds. And these are the basically the prior ranges and the various ranges of the parameters that we obtain. So this exercise actually shows that, I mean, what we have tried to do is directly we have tried to map the model parameter space onto the PTA data, okay, and derive constraints from it. So when we take the best fit, this is how the spectrum would look like in the two cases, that is including with or without including SMBHB contribution. And what we see is that if this is really because of the domain walls, there would be like in the future upcoming observatories, we should be able to observe this signal, and maybe that would tell, it would be a complementary probe to say whether it is really, I mean, we can verify this later. Okay. So yeah, so then these are my conclusions. So gravitational waves are from domain walls sourced from DLRSM could be a possible source of the PTA signal. Okay. And we argued that there are actually two kinds of domain walls in the initial domain wall network, while one of them is unstable and quickly decays, and that's why the structure, just the domain walls evolve only are the left-right domain walls. And we performed a Bayesian analysis using the NG15 data for parameter estimation. And it would also, if true, the signal would also be detected by upcoming gravitational wave detectors. And one last point which I want to make is that while we have done our analysis using DLRSM or the doublet variety, we can actually do almost the same techniques. We can use the same techniques also in the triplet case. So yes, that's it. Thank you.
Thank you, Dhruv. Those are some very interesting results for me, but I'll go to the audience for questions.
And thanks for the nice talk. So could you please elaborate how did you get to Z2? You are imposing one parity symmetry and another Z2 is generating after symmetry breaking or something like that?
I think that Z2 is already there in the rest of the gauge group.
So
So, okay. What I mean is that Z2 could be a subset of this.
okay, so okay, I'll talk to you.
Yeah, I mean, I'm not sure actually how it exactly comes up because, but I mean, it comes. What I feel is that it comes from this. But
Okay, I'll talk to you.
So in your analysis for the gravitational wave, for example, you have not considered the scalars talking to some matter sector, right? Fermions and gauge bosons. But in a realistic model like you show, there would be probably fermions and gauge bosons, which would, I would imagine, modify the entire spectrum of the gravitational wave, especially from the friction, because the matter would contain in the plasma, right? So do you have any idea how much the results would change once, because now that you are talking about a model, you know what is the exact matter content and what is the exact thing to do for the simulation.
right. So yes, that is true. I have not taken friction into account, and I would really have to look it up. I can't comment right now.
So I have a naive question. Like you are saying that you are doing a Bayesian analysis with PT Arcade.
Yes.
So you are running it in enterprise mode.
In that other mode, Cepheid mode.
Cepheid mode.
Yes, yes. So I tried running it in the enterprise mode also, but I think it was taking a lot of time and there were some issues. Actually, right now I don't recall exactly.
Okay. But in Cepheid mode, I think they do not give the Bayesian evidence, right? Bayes factor.
Yeah, Bayes factor they do not give. So what I did is actually this Bayes factor I did not calculate. I mean, this Bayes factor is already there in the models where in the papers where do a comparative analysis of different models. So those I have just quoted the Bayes factor from there.
Thanks.
So for a relative, I just wanted to see what is the difference between these two models that I have considered, essentially for the sake of completion, and I wanted to compare them. So in that case, I just took the delta log likelihood, and from that. Yes.
I just have two quick questions. One is that you're adding an explicit symmetry breaking in order to bias the domain walls.
Yes.
Is that explicit symmetry breaking compatible with the gauge symmetry? You're not also breaking the gauge symmetry when you add the explicit symmetry breaking, are you?
I think you can add operators, basically higher dimensional operators, which respect the gauge symmetry and only break the parity symmetry.
That's what you're doing?
Sorry?
Is that what you're doing?
Yes, I assume that it can be done, and there are many papers who have actually constructed such operators.
But you're not.
I have just
you
taken
didn't
the
write
thing
down-
as a free parameter. Yes.
I see.
Because, I mean, even if we can argue that there is some logic behind it, actually for this analysis, it won't really affect. I mean, what I mean is the origin of that V bias will not change any of the results that I'm showing here.
I mean, if the discrete symmetry is a discrete gauge symmetry, then you can't break it because it's a gauge symmetry. But if it's not, if the discrete symmetry is not a subset of the gauge symmetry, then you can add some operator that'll break it. I think that's what I was getting at.
Okay, so
We could also chat after. I had one other quick question, which was
because
about...
I actually do not understand the difference between a discrete gauge symmetry, and I'll be honest with you.
Okay, that's fine.
So,
and then the other question was about the idea about the, what did you call it, Z2 domain walls fragmenting into LR domain walls. But wouldn't it be more accurate just to say that you never form Z2 domain walls in the first place? Because during the phase transition, as the field is relaxing, I mean, I assume that you're imagining some Kibble mechanism where the system is thermally restored at the origin, and then as the temperature goes down, it relaxes. But wouldn't the system just relax into a configuration that never formed the Z2 domain walls? Like the field would slip around the hilltop?
Right. So actually, when you go to very high temperatures, when the symmetry is restored, so so you are basically coming from that potential and dropping to one of these minima, and these are all degenerate. And if you look at the distance from the origin, it is basically a Z4 symmetry. Okay, so they are all equidistant from the origin. So you are equally likely to drop into any one of those minima.
What I meant was during the phase transition, the effective potential has these minima a lot closer to the origin.
Yes,
and
that
then
is true.
The field will try to relax, and in some point in space you may go left, in some point in space you might go right, but then the field in the middle will quickly recognize that it doesn't want to be at the hilltop, so it'll probably slip around the hilltop.
That is true, but still it will remain that the four minima are equally likely, right?
Yeah.
Yes. So as long as that is true, then you would have both kinds of domain walls.
Okay, I see. Yeah.
Thanks again, Dhruv.